In this final part of Electricity 2, we're going to look at how the dimensions of a resistor affect its resistance. So I better draw a resistor, and we'll imagine that it's a wire like this. So it's got diameter D, which we might show like that, and it's got length L, and that means it's got radius R, and we know that D equals 2R, so that's quite simple. And we also know that the area of the end, which is known as the cross-sectional area, it's not the surface area, it's the area across. The cross-sectional area, A, well, that's equal to pi r squared, or pi d squared upon 4. The reason why we have to divide by 4 is because it's r squared. So since r is d upon 2, when you square it, you get d squared upon 4. And I'm just going to change to a red pen briefly, just to sort of shade in this area here. That's the area that we're talking about. Now, it turns out that there's two very simple relationships. Well, the first one's very simple anyway, and that is that the resistance is proportional to the length. So if you double the length, you double the resistance. If we were to draw a little graph of that, then resistance against length, twice the length, twice the resistance. So that's relatively simple, because this little bit is a little bit harder. It also turns out that resistance is proportional to 1 over the cross-sectional area. So that's a different sort of graph. That means that if we plot a graph of resistance against area, then it sort of looks like this. As one goes up, the other comes down. Or we might say, well, yeah, but hang on a minute. Can I squeeze in another graph? We can just put another one here. If I plot a graph of resistance against 1 over area, then you get a straight line. So the first relationship, resistance is proportional length. You double one, you double the other. Whereas with this one, if you double one, you halve the other. So another way of looking at it is that the resistance times the area is constant. So resistance times area is constant. Because we can see, let's just have a look at it. If you halve the area, then you double the resistance. So we see that the product of the two, the one times the other, hasn't changed. Now, what happens then if we double the diameter? So if we double the diameter, okay, so d goes to 2d, then the area goes to 4 times. Can you see why that is? It's because the area is proportional to the diameter squared. So if we double the diameter, then d squared goes up by a factor of 4. Let's just look at it. Suppose d was 1, and then if d doubled and became 2, then 2 squared is 4. So if we double the diameter, or the radius, then the resistance will go down by a factor of 4. Now, we might just pause to think, why should this be? And if we imagine those electrons going along inside the wire, then the further they've got to go, then the more collisions they're going to have with other things in the wire, the atoms, and therefore the more energy they're going to lose, so therefore the more resistance it's going to be. So that's explaining in a nutshell a sort of qualitative thing as to why the resistance would go up with length. The resistance goes down with area. Well, there's more room for them and they can travel more slowly, these electrons, so therefore they lose less energy if we have a bigger diameter wire. So that ends electricity 2, and that's all we need to know about electricity. Thanks very much for listening. It's time to try some examples. So there's some multiple choice question papers for you to try.